his name. So I need Fernando to pronounce his name. So our next speaker is
Iñaki Garcia Etxebarria.
And he will tell us about new n=1 dualities from contracting orientifolds.
Thank you very much. I would like to thank the organizers for a very nice conference and for pronouncing my name properly. It happened very often. Yeah, so it has been a very interesting conference, and I want to talk about something which is very related to some of the talks we have seen here. In particular, there have been some talks about brain-such singularities, and this is related to some formal aspects of brain-such singularities that we have found and I think are quite interesting. This has been work in collaboration with a couple of people in Cornell, Ben Heidenreich, who's in the audience, and Tim Brasse, who's not. So I'll be talking about dualities in field theory and string theory. And here I just listed some famous and very well-known dualities that we know coming from string theory. So the one I'll be focusing on here is type 2b. In type 2 you have the SL2C and SL2C duality that gets inherited to n=4 four-dimensional theory that also has an SL2C symmetry, or duality rather. We also have T-dualities or mirror symmetry, IDS, CFT. And in the context of n=1 theories, the class of dualities that we understand best and the largest class that we have is cyber duality, which is sort of a generalization of the idea of duality. The duality is not exact, but rather we have two UV descriptions, which are in general different, but they flow to the same infrared conformal fixed point, or the same physics. Here I want to study a class of dualities that seem to be closer actually to n=4 rather than cyber duality. So hence the title. This is why we call them new. They seem to be, well, the dynamics at least in string theory seem to be very new. At least in the context of n=1 compactifications. So let me remind you of how n=4 appears from string theory from type 2b. You can obtain the dualities of SL2C of n=4 by engineering the n=4 theories with O3 planes and D3s in flat space. And there are 4 versions of the orientifold. I've called them O3 plus minus with or without hat. So Witten gave a very nice argument that classifies these theories. What you do is you put the configuration with O3s and D3s in a point, and then you surround the point with a sphere and measure the Ramon 2 form and the Nelson 2 form, and you see that the thing that classifies these forms topologically lives in a C2 group. So C2 cross C2, that's 4. These are these 4 possibilities. You can plot the theories that you get in this graph depending on the type of the orientifold, and if you look at the low-energy theory, you'll find that you find this class of theories. In particular, here we'll focus on these two pair of theories. I'll mostly talk about these 2 pair of theories. So you have an SO2n+1 theory that, if you take the strongly coupled limit, becomes the USP2n theory. So this is a particular case of the n=4 duality in 4 dimensions that exchanges these 2 groups. Right. So Ben gave a very nice talk a couple of days ago about the duality or the field theory aspects of the duality that we have been studying. I'll just quote the results here. So we propose that these 2 theories here, I'm giving here the matter spectrum. So we have 2 gauge groups, 2 gauge factors, USP and SU, and then some flavor symmetries, in particular non-abelian SU3 flavor symmetry. And we propose that this theory is dual, in some sense that I will define shortly, to this other theory in which the SP group becomes an SO and the symmetric becomes anti-symmetric. And then the global charges also change slightly. And something that's rather mysterious, at this level at least, is that in order for these 2 theories to match, you actually have to relate n twiddle and n by n twiddle is n-3. You can do the classical checks, and we checked in various quite involved situations that global anomalies, the modular spaces, and the spectrum of operator matches if you take this relation. So everything seems to work very well. And I can't resist talking about something that Ben couldn't talk about because he didn't have enough time, which was the superconformal index matching. One way that you can, since 7 years now, has been a very powerful proposal for studying duality in field theory. What you do is you take the 4-dimensional theory and you put it in S3 cos R, and you compute a Witten index. This was proposed by these groups of people. And Well, you take the theory, you compute this with an index. You see that this is with an index, so you have some supersymmetries. You want to commute them, you get something that looks like a Hamiltonian. So here, in this part, you see the usual expression for the Witten index, minus 1 to the f times the regulator. And then you have some global symmetries, which I will not discuss in very much detail, except for the fact that you have a T here, which is a chemical potential. So T, X, F are chemical potentials, essentially, for the symmetries of the theory. R you can think of the R symmetry, J3 as some rotation in the 3 sphere, and F is just the flavor symmetry. And then since we have some gauge dynamics, we also have a gauge group, but we integrate over that to get singlets. So if you compute this index, and Rummelsberger gave a very nice prescription in this paper how to compute the index, you can do an expansion in T, for example, if you cannot compute the integrals explicitly, which is very hard. But it's not very hard to expand the index, and you get these kind of expressions in terms of the chemical potentials of the symmetries of the theory. And here what I'm writing is the group characters of the. This would be an F. I'm sorry. You get an expression in terms of the flavor element. So here I'm listing the representations under the SU3. So you see that I'm getting a very complicated characteristic polynomials. So I'm just quoting this result to give a bit of extra evidence, which is less classical than what people generally does, and we check in these theories, and it works very well too. And this is very impressive, at least to me. And you see this, you get convinced that the field theory works, and then you try to understand what's going on behind the duality. So for getting this weird n2 that has to be n minus 3, this seems to be very close to what happens in equals to 4. So SO goes to SP, symmetries known to antisymmetrics. It sounds very similar, but of course, we wanted to understand what's going on microscopically, why was the change in rank, and how to derive this, if this is some kind of S-duality, which seems reasonable, how to derive it from a 2B construction. So of course I'm trying to study something which is branes at the singularity, has strong alpha prime corrections, and I want to go to large GS. That seems hopeless. So what I'm going to do is blow up, go to large volume, and study S-duality in large volume, and then come back. So I'm going to reformulate the problem in terms of objects that I understand at large volume, and then use the usual F-theory rules. I say usual, but we have to work out some new rules that we'll present now. And just to mention that already embedding the configuration in string theory tells you something very interesting about the spectrum of dualities that you expect just by repeating what Witten did. So now we have a brane n equals 1 configuration of branes at singularities. The thing that you need to surround the geometry by is different. It will not be NS5 anymore, but you can compute this twisted cohomology again, and you again get C2s completely compatible with what you see in the pattern of field theories. But I will not dwell on this. So that was the introduction. I'll give a little bit of review of the derived category, since this is a stream pheno workshop and somebody has to mention the derived category. So I will explain what the difference, how to translate difference between small volume and large volume, and then how do you apply this general technology to the particular refold I will explain, and then understanding at large volume what S-duality does in those branes. So as I was mentioning, you take the branes at singularity and you want to see them as large volume objects. Just sort of think in the opposite way. So you start with large volume objects and then take them to the quiver point. And as you do this, the branes and the classical expressions for supersymmetry and things like that get strongly corrected. You do strong alpha prime corrections. In particular, they correct supersymmetry and the masses of states. That's something that Bord mentioned also in his talk. But we can still think of the object in large volume terms. If you have enough control over these changes in the mass spectrum, you can still think in large volume. So that's what we will do. And when you want to think about this properly, Douglas explained that the thing you have to use is the derived category. Well, we did have to care about the subtleties, but here, for me, the brane is just a bundle. So I will give you a manifold, which is P2. I'll put a bundle on top, which will be a classical bundle. And then there will be this number in brackets, and the only thing it does here is distinguishing branes from anti-branes. So when n is even, you should think of this as a brane, and when it's odd, you should think of this as an anti-brane. Right. So we have the thing in large volume. I'll give the example for our refold very shortly. Now you need the action of the orientifold on this object. So this was worked out in the absence of a B field by this group. They give this recipe. So take the bundle, dualize it, tensor by the canonical class, and then, well, yes, change this number in a particular way. You notice it sends brains to brains and anti-brains to anti-brains, so don't worry about the exact change too much, just to be precise. One small thing we had to generalize is that in the presence of a B field, you have to generalize this slightly. So the B field in the presence of an orientifold is half integral. You can construct a line bundle associated to orientifold, and the recipe changes by tensoring with this line bundle. And this is part of a very interesting bigger story that will be in the paper. Alright, so how do we apply this to the our very familiar geometry of brains at the C3 mod Z3 singularity? Well, when you put the D3 in this singularity, it splits into 3 fractional brains. If you use the usual technology for staying with the fractional brains at a large volume, you end up with these objects here. So 2 line bundles, which are both brains, O-1 and O-2, and a line bundle here, which is an anti-brain, and it's the cotangent bundle. So here, omega denotes the dual of the tangent bundle. When you go to a quiver point, these 3 objects become mutually supersymmetric and then form this quiver. We are taking this orientifold involution, so we want to check with the rules I gave before that well, this brain stays invariant and these 2 get mapped to each other. So you just plug them in the formulas, for example, for the bottom ones, these 2. So you take O-1, you dualize it, you get O1, you tensor by the canonical class, in this case just O-3, so you get O-2, which is precisely the other guy. So these 2 get exchanged. And for the invariant one, you do the same thing. It's a little bit more complicated, but it's still very easily doable. You take the cotangent, you dualize and become the tangent, tensor by the canonical class, and this becomes the cotangent again. So this is invariant. You can compute also the chiral multiplet, etc. One thing that will be important for us is that you can also compute easily the charge vectors, the Ramon charge vectors. So you use these expressions worked out in this paper. For the D brains, you compute these characteristic classes. Here you can see the brains and anti-brains, as I mentioned before. When this is even, you get a +1 here, so you get the usual expression. When this is odd, you get a minus. And for the O-plane, this has been worked out also in this old paper. Well, these expressions are not entirely correct when you are in F-theory, but for the cases that we study, they will be correct. Recently, some people have worked out the subtleties. Okay, you plug the brains that we have into those expressions, you get these weights, also for the orientifold. And the reason why I mention this is I want you to notice a couple of things mostly. First of all, if you add the 3 fractional brains, you get the hyperplane. L here denotes the hyperplane of the P2. You get the hyperplane square, which is the class of the D3. This is the usual statement that the 3 fractional brains add up to a regular D3. Okay, so you can check that explicitly here. And the other thing that's important is how do we cancel tuples. So it depends on the sign of the orientifold. If you take an O7 plus, which has positive charge, you want to cancel the charge with an anti-brain. So we'll take the 4 times the cotangent bundle, which was an anti-brain, so this will cancel tuples locally. I should mention that the cotangent bundle is rank 2, so you should think of this as 8 ordinary D7 brains locally. So an O7 plus 8 brains, that's canceling tuples locally. And if you have an O7 minus, you want to use brains, so we'll use the UN brains. So in the case that you have the O7 plus, you have O7 plus the invariant guy plus D3 brains, as many as you want. And that gives you this. So SP4, the 4 comes from invariant brain, and then you can add D3s and tilde D3s, and you can construct the other factor in the same way. So you get 4 of the U brains. Now you use the non-invariant ones, and then you add D3s, so you end up with this expression. Okay, so we can reproduce this. It's not very exciting, but I just wanted to lay down the rules of the game. These are the brains that we care about: the cotangent bundle and these 2 line bundles. Okay, so now comes the physical argument. I want to argue that this duality. How am I doing with time?
15 minutes.
Oh, I have plenty. Okay. Okay, I think I'm going to use the backup slide. So the duality as an S duality. I want to argue that what we are seeing here in the field theory, in the local configuration, is actually an S duality inherited from type 2B. So for this, I need to to make the argument in 2 steps. First, I need to understand what happens to the O7 plus at the strong coupling, and then I will apply that to our particular configuration. So I will study a problem in 8 dimensions, really, just what happens purely to the O7 plus in flat space, and then apply that to our curved background. So the problem with this is that nobody had done it before. So the O7 plus at the strong coupling the O7 plus already in F theory is a mysterious object. We know some things about that. So as Witten explained, the O7 plus is given by a frozen, not clear what freezes it, but some kind of flux freezes a singularity with D8 monodromy. And at the level that we will study these things, we will care only about this D8 monodromy. So in order to reproduce the monodromy, we'll put a system of a B, C, and A to D8 branes. So A is an ordinary D7 brane. Here I'm putting the PQ labels. So we have a 1-0 brane. B is a 1-1 brane, 7 brane, and C is a 1-1 7 brane. So if you notice, this is the O7 minus. Well, I don't know, if you're familiar with these things, this is the O7 minus, and then I am adding the A branes until I get this monodromy. The full story is more complicated. This is a slight oversimplification. And the problem seems to be that in M theory it's known that the O7 plus lifts to not to a D8 singularity, but to something which has a D4 cross D4 structure. So the resolution seems to be that the O7 plus lifts to a non-biased Strauss model, but I think the details haven't been worked out. I will just assume that this is a workable assumption for how the O7 plus is behaving. At least the monodromy is right. That seems to be the most topological thing that you can look at. All right, so let's do S-duality. We have this configuration. If you do S-duality, the rules are well known. We start with this. You act with S-duality, you change P with Q, and one of them changes sign. So 1-1 goes to 1-1, 1-1 goes to 1-1, and the D7 branes go to 0-1 branes. Right. So I want to argue that the dual of this is the same thing as O7 minus with 4 A branes plus 4 0-1 branes. This is our proposed dual. So how does this work? Well, the dual I just wrote, this one. Let me take these 8 branes here and split them in 2 groups of 4. And then I will play around a little bit with the positions of the branes. So these are branch cuts. I take this convention, they go downwards. If you cross this brane along these branch cuts, it stays invariant. So you end up with the same brane on the other side. And in the new configuration, if you take these branes below this branch cut to this new position, this 0-1 becomes 1-0. So this is a very simple argument in F theory that tells you that the O7 plus at the strong coupling looks at least very much like this configuration here. Okay, so how is that useful? This is something generic. So if you try to do S-duality, the reason why S-duality typically doesn't give you anything simple in n equals 1 theory is essentially because of this kind of things that appear here. So you get a non-perturbative brane and you don't know how to describe this easily. In our case, there's some kind of very nice cancellation I will show now that sort of removes all the complications coming from here. So how does this work? So the previous argument was just flat space. If I want to go to our curve configuration, what I will do is just model the A branes, the ordinary 7 branes, but the closest thing that we have, which are these 2 invariant D7 branes. So I will claim that the O7 plus goes to O7 minus plus the 4 A branes plus the 4 0-1 branes. So the hat just means a magnetic dual. And since we are compactifying and you get some induced charges, etc., you need to compensate for the extra D3s that you're introducing. And I will add n D3s here. D3s are SL2C invariant, so this is not a dangerous thing. So if you just compute charges in both sides, you'll find out that n is -5. Using the formulas I gave before, that's what you get. All right. So if we take the configuration we started with, the O7 plus the 4 cotangent bundle branes, anti-branes, right? Plus the, let's say, n-twiddle D3s, what you get is the O7 plus goes to the same thing as before. Now the 4 cotangent bundle goes to the magnetic dual of the cotangent bundle. So you get this combination here. You still have the -5 branes that appear here, and you have the D3s, which are SL2C invariant, so they stay D3s. So you get you get this on the S-dual side. Another nice thing that you realize is that all the complications seem to cancel, so you get a bunch of magnetic branes, but they are exactly the 3 fractional branes for the magnetic D3. The D3 is SL2C invariant, so you can rewrite this whole chunk here as 4 D3s. So n tilde minus 5 plus 4, that's n tilde minus 1. And if you now read the field theory, what you have is, we started with O7 plus with invariant branes, so that's USP4 plus n tilde, so USP n plus 4 plus. And now you read the answer on the dual side after you do this process, and you end up with, well, you get, let's see, from here you get a plus 4 on the non-invariant side, so you get 4 more branes here than here, and the invariant branes come purely from here, so you can read the rank. You see, SO n tilde minus 1 goes to SU, sorry, cross EU, SU n tilde plus 3. Let me conclude. I think we're ahead of time. So we found a new class of possible n equals 1 duals. This is a duality that seems to follow from S duality by this simple argument I just presented. We seem to have many other examples in which the same story applies, other phases of field theories, del pecho, so this is a nice thing that we can access things which are non-toric, so which are non-toric and non-orbifold, so it seems to be a very general story. We also have some orbifold examples in infinite class, in fact. I think that's very nice from this analysis is that we develop tools for analyzing orientifolds at a small volume. This should be useful, I think, for studying branes at singularities if you start putting orientifolds, which sometimes is useful for phenomenology. So essentially what we did is connecting this paper here, where they study orientifold at large volume, how it looks in terms of the derived category. We connected with the discussion in this paper, where they present the result in terms of dimers. So now we have a sort of first principle connection between these two things. We also got some information on the strongly coupled behavior of the 7 plus, although this is still a little bit mysterious. So I had to give some jumps in the argument, but I think they are physically sensible. So it would be nice to work out the details, but I'm convinced that this is right. Okay, so that was all. Thank you.
Thank you very much. And we time for questions.
So you propose a way of realizing your 7 plus in FQ,
Well, at the level of,
yeah, I'm puzzled by one thing. So you said that the monodromy of your 7 plus is somehow like the D8 singularity.
Yeah.
But why is that? Because I expected just the 7 plus as opposite charge in the 7 minds. Is there a simple way to see?
Yeah, you can. Yeah. So let's see. So you have the thing that cancels tadpoles locally. Cancels monodromy locally. That's the D4 singularity. So that's the -1 0 0 -1 monodromy matrix, and then you're adding 4 branes. So multiply that by 1 4 0 1, and you get precisely -1 -4 0 -1, which you can check it's the matrix of the 8.
More question.
Question. Many times this number change of branes is related to some Hanani-Witting type effect.
Yeah.
Do you have some understanding in that direction?
In the beginning we thought it could be something like that, because usually this kind of dualities in equals 1 appear from motion in moduli space and Hanani-Witting, as you were saying. And the reason we are claiming this is qualitatively different is because there seems to be no realization in that way. The moduli space is very simple, and there's not really motion. It's not like a monodromy and you come back to something else or you go to somewhere else. You stay in the same point and you just crank up the coupling. Do something else. So that we didn't find any realization along those lines, and I think it's not. It's a different physical process.
More question. Let's thank our speaker again.